For RCR TV, I'm Sean Kinney, and welcome to HetNet Happenings, where we talk about all things DAS, Wi-Fi, small cell, and much more.
CommScope, thinking beyond today's technology to help you make the best decision for your network and your business. Register today for the Wireless Infrastructure Show, the premier national event for mobile network solutions, produced for the industry, by the industry. Telecom Careers, the #1 global telecom and wireless job board, telecomcareers.com.
All right, welcome back to HetNet Happenings. You know, I say in the show tagline that we talk about all things DAS, small cell, Wi-Fi, and much more. Today's show decidedly is going to fall into that much more category. We're joined by Robert Heath. He's a professor of electrical and computer engineering at the University of Texas at Austin, as well as a member of the Wireless Communications and Networking Group. Robert, I wanted to, well, first, thank you for joining us. We really appreciate you coming into the studio. But I wanted to talk about just a few different aspects of your research, and if you don't mind, we'll jump right in and talk about MIMO, multi-input, multi-output.
Okay.
This sort of configuration in a wireless network will put multiple antennas at the transmitter, multiple antennas at the receiver, gives a few different benefits to a mobile network operator. So how does MIMO benefit a mobile network operator in terms of capacity and spectral efficiency?
Yeah, it's a good question. So, I mean, MIMO, the original interest in MIMO really came about because of the spectral efficiency. And so by having, base stations typically have a lot of antennas. By putting a few extra antennas on the handset, you can increase the spectral efficiency and so increase the peak throughputs that the users see.
And so in terms of capacity, what do I get differentiating between MIMO and no MIMO?
Well, the theory would be something like a 2 or a 4x if you had 2 transmit, 2 receive antennas, or 4 transmit, 2 receive. It's been a bit more problematic in cellular because a lot of these things depend on the positions of the antennas as well as if there's interference or not. So the practical gains from MIMO, the gains that everybody sees, may or may not be as high as that.
Okay, so to what extent is MIMO used by major carriers?
Well, my understanding is it is widely deployed in at least what we call the 2x2 configuration with 2 streams, so 2 transmit antennas at the base station, 2 at the mobile station, and it may be just 1 on the uplink. Some more advanced deployments have a couple antennas at the user equipment.
Okay, and I know when we talk about carriers, there's always sort of a veil of mystery because they don't really, tell you what exactly they're doing in terms of physical configuration. But it's not really ubiquitous, is it? It's not everywhere.
No, it's not. I mean, to really exploit MIMO, they potentially have to deploy different antennas at the base station. Depends on how their antennas were configured, and then of course they have to upgrade the processing. And so you would roll it out in markets where the peak rate is going to be more important. And so rural areas, it's not widely deployed, I would guess.
Okay, and you mentioned interference. I know to some extent MIMO can cut down on interference, but to step back from that, and this is something I just don't fully understand that well, can you explain what interference is, what we're talking about when we say interference as it relates to a telecom network?
Yeah. So interference, I mean, generally is an undesired signal. Now, you can think about interference as being, some signal transmission that shouldn't be in the band, but that's actually not very common. So in the licensed bands where people own the spectrum, I mean, it's usually the interference is created from their own equipment. So cellular systems, they reuse the frequencies in different cells, and so when you're in one cell, you receive also signal from other cells, and since that's undesired, that would be considered as interference.
Okay, and does that sort of get back to when we say spectral efficiency? If you can cut interference out of it, do you get a benefit in terms of your spectrum usage, or why do you want to get rid of it?
Yeah, the spectrum efficiency. I mean, especially when you talk about area spectral efficiency, is very important. So I mean, interference. When you're really evaluating the quality of a link, the performance depends on both, the signal power, the noise power, and the interference power. And so if you can increase signal, which normally you can't do because that's limited, reduce noise, which normally you can't do, this depends on the hardware, but you can maybe reduce interference by designing the system or using better signal processing algorithms. And so that gives you better spectral efficiency.
Okay, and we've done some work with the wireless network and communication group at UT before, and I think some of the slideshows I've seen that talk about 5G, sort of the next evolution of cellular standards, spectral efficiency is a big part of that, right? Getting the most out of what you have, since it's a limited resource. So, tell me from your perspective how spectral efficiency is going to figure into 5G.
Okay. Well, I mean, spectral efficiency, it's critical because we do need to basically offer higher rates and support more users. So it's going to factor in. It's going to factor in primarily at the lower frequencies, I think, in what's called massive MIMO, so the use of lots of antennas at the base station and quite a few, serving quite a few users. It's like it's a particular multi-user MIMO configuration.
Okay.
But it's probably not going to solve the problem completely. And I think we're also going to have to go to higher frequencies to get wider bandwidths. So spectral efficiency and spectrum are both needed for 5G.
Okay, and you mentioned the higher frequencies. I know another portion of your research focuses on utilizing millimeter wave, which is that high frequency that we don't really fully utilize right now. So can you give us an overview of millimeter wave? It's something that I have not a totally clear understanding of.
Sure. Yeah, so the carrier frequencies we use right now are what's called the UHF band, ultra high frequency. So there may be 900 megahertz, 850, 1900, 2.4 gigahertz at Wi-Fi. So millimeter wave is above about 30 gigahertz up to 300, but the candidate spectral bands are maybe 28, 38, 48, 72. And so the carrier frequency is higher, but what's really interesting there is that the bandwidths of signals potentially is much larger. So instead of having a 20 megahertz channel, it's much easier to have a 200 megahertz channel or a gigahertz channel. And your spectral efficiency multiplies that number to give you the data rate. So the more spectrum you have, the higher your data rate.
Okay, and I know, millimeter wave gets talked about particularly when you're looking at device-to-device communication, even potentially wearables. How does millimeter wave figure into the particular topic?
Yeah, so that's a topic. I mean, we're looking at also that I think is going to be very important because, especially in the wearable space, you can imagine, the smartphone as being the hub for a wearable network, but it has data to send maybe to your smart glasses, your smart watch. And if you want to stream uncompressed video, you need very high data rates. And again, that's a place that millimeter wave can play a role, possibly in the form of 11AD, which is the unlicensed millimeter wave Wi-Fi standard.
And then, and I think this is kind of what you guys dig into at UT. What are the real challenges to fully utilizing millimeter wave?
Well, there's a lot of difficulty here. Many of them come from the hardware constraints. There's a need to develop hardware that's very low power, so it doesn't use up all of your battery. But when you go to higher frequencies and higher bandwidths, the power naturally gets consumed. And so developing signal processing techniques that reduce the power expenditure, so we can still exploit the bandwidth, we can still exploit MIMO, but we don't have to pay a huge cost in terms of power performance.
Okay, I really liked your example of the smartphone being sort of the hub of your personal wearable smart network, but wouldn't sort of with millimeter wave, wouldn't line of sight be a big sort of challenge to those connections?
Yeah, it's a challenge. There's a few issues there. Well, one of them though is that millimeter wave does work with non-line of sight. So as we were talking, I could be reflecting actually off of you. We are very good reflectors at millimeter wave, so I can actually reflect off of the objects and get a non-line of sight link. The other issue is that there hasn't been a lot of work done on networking on and around body at millimeter waves. There's only a few studies, and so we know pretty well that it doesn't penetrate very much, But
like walls and buildings.
yeah, walls,
okay.
buildings, people. I mean, it depends on the walls,
Right.
but in particular, it doesn't penetrate people very well. That's why they use it for these naked body scanners in the airport, for
Okay.
millimeter wave. But you know, a lot of work is still needed to understand the propagation channel, but we know that it's not always going to be line of sight. So you have
Yeah.
to be able to adapt, can work in non-line of sight, switch to lower frequencies.
Yeah, I guess the way I think about it, I feel like if I'm moving and turning, that I'm
Yeah.
affecting sort of the quality.
Yeah, and that's true. And we've done work on this in cellular, modeling the effects of the human body blocking the signal.
Mm-hmm.
We've also been looking at this for wearable networks, where we look at very dense environments like a train car or a bus, and the effect of every user having a wearable network, but users also acting as blockages. And so the interesting thing here is that while you might be blocking your own signal, other people are also blocking their own signals, and actually the interference environment can be much better. So even though your signal is not as good, your interference may be even much lower. And so in fact, your signal to interference is surprisingly good.
Okay, and this would work off of a tiny antenna, right?
Yeah, it could work off of potentially a very small antenna, but more likely it's going to be a little array of antennas.
Well, yeah, that's what I was going to ask. Is if it's so tiny, you can use a lot of them, right? And
Yeah.
sort of round out the edges.
Yeah, so you can use like the 11AD implementations I've seen at 60 gigahertz. Some of them use up to 32 antennas, and they fit in a small space. You know, could be like the size of a fingernail. And you actually need the antennas because you need to get array gain. So it's not so much like the traditional MIMO spatial multiplexing as it is just to capture energy, so that we get enough receive power to get a good SNR.
And you mentioned the airport body scanners as a use case of millimeter wave. I think we're all familiar with those now
Yeah.
that they've been dropped in almost every airport.
Yeah.
Are there any other sort of actual ready to go uses for millimeter wave, or is it mostly R&D at this point?
Well, I mean, there is stuff in the millimeter wave band that's deployed up to about 100 and maybe 20 gigahertz. So there's there's many kinds of radars. There's satellite links. This unlicensed band at 60 gigahertz is being used for personal area networking, and it's also going to be used for Wi-Fi. I mean, these products are available now. The HDMI cable replacement has been available for about 5 years, and then the Wi-Fi products are starting to ship now there. So there's a lot of consumer products. There's like automotive radars at 77, and then there's just a lot of other, the military, satellite, non-commercial wireless applications.
But for full scale sort of, utilization of this in cellular, what needs to happen?
Well, we need quite a few things. I mean, one thing we need is some spectrum, but I think before that we have to convince, FCC and others that it's viable, because it's a long process to get spectrum. Because even though that a lot of the spectrum is not very well used up to about 110 gigahertz, but it's still licensed, so someone has it and won't want to give it up without some compensation. So we have to demonstrate that it's going to be really worthwhile, and that's a lot of the research that we're doing at UT, and my group in particular, studying the effects of if you go to millimeter wave, how does that improve cellular system performance. And FCC has released this notice of inquiry, which many people responded to, about the viability of using millimeter wave for cellular. And my group submitted a response to some of the comments there. And we're very, very much in favor of millimeter wave for cellular. So we think it has a lot of potential.
And does millimeter wave have any sort of, and I know we're talking down the road here, but from your point of view, does it have any sort of implications for what a 5G standard might be?
Well, using the millimeter wave, it'll potentially change a lot of features of the standard, because it might need a different physical layer. It might not use OFDM, it might use MIMO a different way. The multiple access strategy would be different. Because you need directionality in the antennas, a lot of the things we take for granted, like when you first power your phone on, the phone listens for the base stations. But if the base station has to point a beam to you, but you just turned your phone on, how does it know you're there? So there's a more complicated procedure for telling the base station I'm here, when the base station can only hear in little directions. So it's had potentially a lot of changes in the standard. The other thing is going to be the role of density, because our work has shown that you probably aren't going to use millimeter wave for very large cells. So in urban areas, maybe 100, 200 meter intersite distances. And so it's kind of a natural companion for the, for heterogeneous network, especially the small cell, femtocell.
Okay, so how would a small cell interact with a millimeter wave antenna in a sort of hypothetical use case?
Well, in a hypothetical use case, the small cell has a millimeter wave array, and it's doing millimeter wave itself.
Okay.
And in fact, the macro might be doing communication at the lower frequency. So you could imagine that in the two tiers, instead of sharing the same spectrum, maybe the second tier, the small cell tier, is just using the high frequencies, and the macro just hands off people to high frequency, high bandwidth hotspots as needed.
Okay.
And then a nice thing about that is that the macro can handle some of these control functions that are difficult to do purely at millimeter wave.
Okay, and you mentioned ultra dense networks, and these obviously show up in metropolitan areas, big cities, and particularly the densest parts of big cities. So how does this continued densification of urban networks contribute to 5G thinking and research?
Well, I think there's a lot of belief that density is really critical, because to get area spectral efficiency, which is bits per second per hertz per meter or per kilometer squared, you need a lot of infrastructure. And so I think density is a big part of a 5G solution, but the reality is it's a big part of 4G as well.
Yeah, and I guess that's kind of, I'm curious, it seems like as the R&D for MIMO and millimeter wave continues, it seems like it could be used to maximize what we get out of LTE as we more broadly move towards 5G. Is that fair to say?
So in the sense of in millimeter wave, you say, or?
MIMO and millimeter wave, all the stuff that's R&D is geared towards 5G, but it seems like it can also help us sort of extend the utility of LTE.
Yeah, I think that's a fair observation. And I mean, there's it may be that there's just an evolution of LTE that eventually becomes 5G.
Right.
If we just keep adding antennas at the base station, for example, using massive MIMO, sticking with the frequencies we have now, then we could support more users, get more spectral efficiency, and at some point, maybe someone could declare, hey, that's now 5G.
And and we've talked this whole time about how all this stuff feeds into 5G, and before we got on the set here, you and I were discussing this 5G summit coming up in Brooklyn that Ted Rappaport is putting on. What is sort of the state of 5G R&D right now, if you could just sum it up for us?
Well, every company, big player here is, got a research agenda in 5G. So all the major carriers, all the major silicon providers, carriers, network providers. So everyone's looking at it, trying to figure out what it will be. The standardization efforts haven't fully started yet, maybe be another year. But in particular in the US, we do not have a really coordinated effort right now. There's not for example, large NSF, ERC type projects funding this. There's not a lot of coordination between academia and industry about 5G in the US. In contrast to Europe, where there are some really high profile big projects funding academic research, and there's a little bit more of a tighter connection. Now at UT, we do have a lot of collaboration with industry, but it would be great if we had this on a large scale in the US.
Yeah, and I know China Mobile and some of the other big Asian players are also sort of following their own research agenda too. So it's kind of, it's hard to me to really think that a 2018 sort of small commercialization followed by more broad in 2020 is realistic. What do you think? Is that?
Well, it's going to come down to how and who defines what is 5G. I think a millimeter wave deployment at those frequencies is optimistic because we don't have the spectrum yet. It's possible we'll get it, but it seems like it may take a few more years. But you could have a lower frequency solution that someone baptizes as 5G come out. And that'll probably be what happens. Whatever's around, someone will say, hey, this is now 5G.
Yeah, and I feel like without the coordinated development of the standard, basically the first person to market with something that's new and different is going to kind of corner the 5G as a marketing term as opposed to an international standard. Yeah.
Well, I think, it is going to be developed in the context of an international standard, but right now, the research is just, it's in that initial phase where it's going in a lot of different directions. But I mean, the companies, of course, are going to develop a standard. Doesn't make a lot of sense for them to develop a proprietary cellular solution.
It's I'm interested to see what happens, but I remain slightly skeptical of these firm dates. I'm just really curious to see what happens between now and then.
Yeah, I agree. Yeah.
All right, Robert. Well, I appreciate you coming in and filling us in on all the research that you and the rest of the folks at UT are doing. Also want to put in a quick plug. I know that you and Ted Rappaport, who we mentioned earlier, wrote a book that's available on Amazon.com. What's the title?
I think it's Millimeter Wave Wireless Communications.
There you go. So if you want to know more, you can check out the book. And for a lot more news content, multimedia content, please check out rcrwireless.com. Thanks for joining us on HetNet Happenings.
HetNet Happenings is a production of RCR TV. To reach Sean Kinney or to suggest a show topic for HetNet Happenings, you can reach Sean at skinney@rcrwireless.com. On Twitter at Sean Kinney RCR. To find out more about the latest in HetNet and all things wireless, dig into rcrwireless.com.